this video, we're going to just do a brief overview of regression analysis. So regression analysis you can think of as curve fitting analysis. Okay, so if we have a variable y that's a function of at least one independent variable x. Okay, so we say y is a function of x. Right. Um, all right. Now, if we don't know the relationship, uh, yet between x and y, but we have a data set of x and y, so we have a set of data points of x and y, right? We can use at least regression analysis to determine what is our polynomial that will describe the relationship between x and y. Okay, so we can say that polynomial can be shown below. Okay, where we have a certain number of coefficients. Okay, so in this case we have coefficients a, all right, 0 through a m. Okay, so this gives us m plus 1 coefficients, okay, of our function. All right, so what we can say is that we can take the value that we estimate for y, which we say y of our correlation yc, and we can look at the difference between that and the actual value at each value of x, and we can call that difference the deviation. Okay, so the goal of the least squares method is to minimize the deviation at every point along our independent variable, along every value of x. Okay, so if we can take the partial derivative, right, of y of c with respect to each unknown coefficient, so we take the partial derivative of yc with respect to each unknown coefficient. All right, so we can do it with respect to a0. All right, Alright, and we have each unknown coefficient. We just keep going all the way down until we have a bunch of equations until we get dyc with respect to a of m. Alright, we have all these different equations. Okay, alright, each of these equations has m plus 1. We have m plus 1 equations, and we have m plus 1 unknowns. Alright, in these cases. Alright, and we can solve for those. Okay, so, alright. So there's a few different terms that we can go through, or a few different ways we can talk about how well uh, a line fits a certain set of data. So one way to do it is we can use something called the standard error of the fit. Right. So how closely a polynomial fits a data set is defined using this equation here. All right. All right. Using that standard error that we just talked about, we can approximate the uncertainty of the fit by dividing that standard error by the square root of the number of data points in our set. All right, and we can again can relate that to a confidence interval using this this equation here. Okay, so we'll do an example problem to determine an equation for the data set that's shown below here. All right, but we can keep going to the next. We'll go to that next. I just want to get through a couple of things here. Okay, so so in the case of different types of data sets, it helps to look at we have to if we it helps to look at to take the data and to plot it on different types of graphs. Okay, so if we have linear relationships, we plot them on two linear scales. Right, we have a linear scale on both the y and the x. All right. In the case of an exponential equation, often we have a logarithmic on the y and a linear relationship on the x. And then for a power fit, we can have log on both sides. Right. So if we actually take the log of both sides of our data sets in both equations, what we end up getting is we get, in the case of a power situation, we get a log term. If we take the log of the y and we plot that, we get again we get a linear line. Okay, um, and and so on and so forth. Okay, so the nice thing about this is that you get these um, equations um, uh, from these, by taking these relationships where you take like the log of the y, the log of the x, and you can actually determine the coefficients of uh, our equations here. So we can determine what is the power, appropriate power, what's the appropriate coefficient, what is the appropriate value, e raised to which power. So in this case it was -1 and the coefficient was 2. You can do that using those linear log relationships. Okay, and then the last thing is if you have a linear polynomial, you can use something called a correlation coefficient, all right, which you can use this value here to determine what the r squared the r value would be. Okay, so if r is equal to plus or minus 1, it's an excellent fit. All right, if any r is between 0.9 and 1, it's a reliable fit. Okay, oftentimes you'll see like the r squared value reported, which is just the r value squared. All right, nothing new there. And you can, it's just a similar metric. Again, if you look at these two results, the r squared would be basically between, if it was between basically greater than 0.81, it's a pretty reliable fit. All right. Um, all right. So we'll do an example problem, an example in Excel, just to show you how you can fit a linear set of data using a couple Excel functions. Okay.